The most exciting part about the quantum internet is that we can't even start to imagine what it can bring to us before it becomes a reality. I'm a quantum engineer. I work on solving problems to create quantum information technologies to enable something called quantum internet. Since I was young, I was always fascinated by the fundamental and the strange properties of light. And that led me to the current field of quantum optics, where we try to gain understanding of the fundamental properties of a single particle of light. We call it photons. And these photons can be used in something we call the quantum internet. Quantum internet is fundamentally different from the classical internet we use today. So instead of connecting digital computers, it connects quantum hardware. The biggest role of quantum internet is to connect dislocated quantum computers, such that the computational power, when they combine several these quantum computers, will be far exceed the power of a single quantum computer. This gives you the sense of you can remotely transfer and process information even though your underlying hardware is distributed over a very large distance. Quantum internet will promise a new way of communication that is essentially unhackable and is protected by the laws of physics. One way to build such a network is to create something called hybrid quantum interconnect. So another aspect we're trying to address is quantum repeaters, which extends the distance between a quantum hardwares. In terms of our ingredients, our daily playing field is about atoms, photons, and solids. We took a very bottom-up approach by creating materials in-house by ourselves. We selectively dope a very dilute amount of rare earth atoms, which have profound properties where they are immune to most of the noise in the environment. So in general, the low temperature environment helps to quiet down the noise coming from the environment. We need millikelvin dilution temperatures to quiet down the paramagnetic impurity atoms. Our experiment is kind of unique that requires both optical access and microwave access at lowest possible temperatures at the bottom of a dilution refrigerator. We do need to do some extra work to mitigate the vibrations that typically present in a dilution fridge. So for that, we work closely with our colleagues at Blueforce, and we custom designed this additional framework that surrounds the fridge to dampen or dissipate the vibrations that are coming from the moving parts of the fridge. We have to make sure that the photons emitted by these two atoms will meet somewhere in the middle of these fibers exactly at the same time. And that's something that requires quite a feat of engineering. Quantum information science technology is still by large at this infancy stage, and therefore there remains many unknowns and many uncharted territories. Almost on a daily basis, we're expanding the boundaries of existing human knowledge. At the same time, this expansion of knowledge can also potentially lead to something useful as an application, as an engineer. And that's something tremendously exciting for me, that we're both playing the role of a scientist to making understanding of how nature works, at the same time try to create something useful for technology. That's something that keeps me wake up every day to come to the lab and I work tirelessly with my students and the teams.